Today we are going to continue talking about derivatives as being rates of change of a function. Recall in the previous section that we defined the instantaneous rate of change of some function f of x with respect to x at some point, x equals x1, as the limit of the average rates of change over smaller and smaller intervals. So again, think about our picture of our curve and our points P and Q, and this idea that as we bring Q closer and closer and closer to P, if we're finding the slope between P and Q of that secant line, as Q gets closer to P and we take the limit of those slopes, we are getting the slope at point P, which is the slope of the tangent line to the curve, or the derivative of the function at point P. So in this situation, they're just calling our 2 points x2 and x1, and the y values f of x2 and f of x1 instead of p and q. But this is the same idea. Since we know that the limit is now called the derivative of f at our point x1, then we know that the derivative f prime of a is the instantaneous rate of change of our function with respect to x when x equals a. So this is just kind of a review of information that we've already had in other sections. Let's take a look at example 1. They are giving us the function f of x equals 2x cubed plus x, and they're asking us to find f prime of a. All right, so this is a situation where we are looking for a generic derivative at any point A that we could then use later to find a slope of a tangent line at any given A value along our curve. So in this case, the formula that we're going to be using is f prime of A is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And we've used this formula many times before. So let's find our derivative. F prime of a is going to be equal to the limit as h approaches 0 of f of a plus h. So 2 times a plus h quantity cubed plus a plus h. And then we have to subtract f of a. So I'll use a bracket here. 2 times a cubed plus a. And again, all divided by h. All right, now we just need to do some algebra and simplify and reduce so that we can evaluate our limit when h is 0. Okay, remember back to Algebra 2 when we did a plus h quantity cubed? It's probably been a while. If you go back to the beginning of your notes, somewhere at the top, maybe above the title, you may want to put a little note for yourself because this is going to come up a lot in the next few days. And it's nice to just know what it is and not have to multiply a plus h times a plus h times a plus h. A plus h quantity cubed, when you FOIL it all out, gives you a cubed plus 3a squared h plus 3ah squared plus h cubed. And if you don't believe me, you can multiply a plus h times a plus h times a plus h, combine like terms, and I promise you that that is the result that you will get. So going back to our limit here, this is going to be 2 times a plus h cubed is a cubed plus 3a squared h plus 3ah squared plus h cubed plus a plus h. And then when we distribute our negative, we get minus 2a cubed minus a all over h. Next step would be to distribute the 2 in our first term. So we have the limit as h approaches 0 of 2a cubed plus 6a squared h plus 6ah squared plus 2h cubed plus a plus h minus 2a cubed minus a all over h. And now it's time to cross out terms that cancel. So we have a positive a and a negative a, and we have a positive 2a cubed and a negative 2a cubed. And all of the rest of the remaining terms contain h. So in our next step, let's go ahead and let's factor that h out right away. So we're going to have h times 6a squared plus 6ah plus 2h squared plus 1. And this is all divided by h. And so now we can cross out those h's. And when we evaluate our limit as h approaches 0, this is going to be equal to 6a squared plus 6a times 0 plus 2 times 0 squared plus 1. So this term becomes 0 and this term becomes 0. And we get that our f prime of a is equal to 6a squared plus 1. In our second example, it says a particle moves along a straight line with an equation of motion, s, which is equal to f of t, is 100 plus 50t minus 4.9 t squared, where s is measured in meters and t is measured in seconds. Find the velocity when t equals 5. So they are giving us a position function, and they are asking us to find velocity when t equals 5. So first of all, recall that velocity is the derivative of position. So if we know we have a position function, then we need to find the derivative at x equals 5 or at a equals 5, whatever you want to, or at t equals 5, whatever variable you want to use. We want to find the velocity when t is 5, so that's going to be the derivative of the function at the point 5. Now since we know our a is 5 or our t is 5, whatever variable you want to use, we can use the formula f prime of t is going to be equal to the limit as t approaches a of f of t minus f of a all divided by t minus a. All right, so specifically for this problem, we are trying to find f prime of 5. And f prime of 5 is going to be equal to the limit as t approaches 5 of f of t, so that's just our function, which is 100 plus 50t minus 4.9 t squared, minus f of a, which is f of 5. So over here, f of 5 is equal to 100 plus 50 times 5 minus 4.9 times 5 squared. And if you grab your calculator and you do the math, f of 5 is equal to 227.5. So when t equals 5, f of 5 is 227.5. So we're going to have minus 227.5. And this is all divided by t minus 5. All right, so I'm going to simplify this a little bit. F prime of 5 is going to be equal to the limit as t approaches 5. I'm going to put my terms in descending order. Negative 4.9 t squared plus 50t minus 127.5 divided by t minus 5. And I know that in order to be able to evaluate this limit, I'm going to have to get rid of that factor of t minus 5 on the bottom, which means that there has to be a factor of t minus 5 on the top. Okay, now I know you're looking at that numerator and you're thinking, I don't know how to factor that. And that's fair. I don't necessarily know how to factor that either. There aren't numbers that are popping into my head immediately because we're dealing with decimals here. However, we know that in order for us to be able to evaluate this limit, there has to be a factor of t minus 5 in the numerator. So I'm going to do a little bit of fancy algebra here. I know I've got this t minus 5 in the bottom. And if I factor a negative 1 out of my terms, then this becomes positive 4.9t squared, negative 50t, and positive 127.5. Okay? So if I know that there's a factor of t minus 5 in the bottom, then I know that there has to be a factor of t minus 5 in the top too. And if I keep that negative 1 here, that means I just have to figure out what goes here. Well, I can do that because I know that whatever is right here times negative 5 has to give me positive 127.5. So I divide 127.5 by 5 on my calculator, and I get 25.5. So this spot right here is going to be 25.5. And I know it has to be negative because a negative times a negative would give me this positive 127.5. And then first times first, so this spot right here times t has to give me 4.9t squared. Well, then that becomes obvious. That has to be 4.9t right there. So I end up with negative 1 times 4.9t minus 25.5 times t minus 5. And now I can cross out the t minus 5s. So my f prime of 5 is going to be equal to the limit as t approaches 5 of negative 1 times 4.9t minus 25.5. And so now I can go ahead and I can plug in 5. So negative 1 times 4.9 times 5 minus 25.5. You grab your calculator, you do the math, and you end up with 1 meter per second. Okay, so that is the answer to example 2. I want to make a little note, and you can put this note anywhere that you have room or in your margin somewhere, but I want to talk about the other derivative formula. We could have done this problem a different way. We could have used f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. And if we had used that formula, we would get a different answer, right? We would get that f prime of a is equal to negative 9.8t plus 50. But remember, that would be an equation for the derivative anywhere on our function. So then if we wanted f prime of 5, f prime of 5 would be equal to negative 9.8 times 5 plus 50. And if you do the math, you get that that is equal to 1, which is the same answer that we got when we used the second derivative formula. So we could have done this problem a different way. We chose to use the f of t minus f of a over t minus a because we knew that t was 5 and we were only looking for the derivative in that one location. But we certainly could have found the generic equation for the derivative and then use that to find the derivative when t was 5. Our final example doesn't actually involve any math. It just asks us to think about derivatives and what they mean. It says the number of bacteria after T hours in a controlled laboratory experiment is N equals F of T. So we have a function representing the number of bacteria after a given amount of time. Part A asks, what is the meaning of the derivative f prime of 5 and what are its units? Well, let's think about what derivatives are. Derivatives are rates of change. So we would say the derivative f prime of 5 is the rate at which the bacteria population is changing. And since it's f prime of 5, it's the rate at which the bacteria population is changing after 5 hours, because it is specific to that time. Okay? The units would be bacteria per hour. And if you know anything about bacteria growth, you know that basically it's just going to keep growing and growing and growing. So part B says, suppose there is an unlimited amount of space and nutrients for the bacteria. Which do you think would be larger, f prime of 5 or f prime of 10? Well, if there's an unlimited amount of space and nutrients, then I would expect f prime of 10 would be greater than f prime of 5 as long as space and nutrients are unlimited, okay? But if our nutrients become limited, this could either slow or stop the growth rate completely. So in that case, f prime of 10 would not necessarily be greater than f prime of 5.